Good afternoon and welcome you all for today's class. Today we are going to discuss about relationship between the pressure, height and density of the water because we have to find out what is the pressure at the depth of water, how pressure varies, and we apply in previous class we have discussed about Pascal's law. Here we use Pascal's law to derive the equation between pressure, height, density and gravity, gravitational acceleration, how we derive because this is a wide application. We have to apply find out pressure, whether it is a manometric measurement, whether it is a piezometric pressure measurement, whether it is a atmospheric pressure. Everywhere this concept applies. So let us see how we can derive equation. P equal to rho gh. This is equation and well-known equation. How we derive this equation? So let us see. Draw a. This is a whole datum. Take a datum. This is a datum. This is a datum. We will measure distance from this datum. Here y equal to this point y equal to 0. And here take a level. Here take level. This is a, here some fluid is there. Some fluid is there. Some fluid is there. This is level. And here pressure is P atmospheric. Pressure is P atmospheric. Pressure is P atmospheric. And take a cylindrical very small cylindrical element. We take very small cylindrical element here. So take a cylindrical element here of dy length. This is a cylindrical element. Length of the cylindrical element is a dy. This is a dy length. And area of this cylindrical element is this area is A. This is area A. And density. This is the density. Rho is density of fluid. Density of fluid. Density of fluid. And here we take this. This is the height y from datum. And take with two reference lines here. This is a y1 point, y1. This is a y1, and take another point here. This is another reference point. We take y2. So this is a cylindrical element, and suppose this is a pressure at this point. Pressure at this point at y. Pressure is a P, and we go up. Pressure at this point here, area is A, and pressure at this point will be equal to P plus because according to height, as height increases, pressure will also change. So del P, it is a function of y, del P over del y into dy. This is a pressure at another end. This is A, B, C and D. So pressure on the face AD equal to P plus del P over del y dy because pressure is a function, and you can see here when we apply pressure on the length according to Pascal's law. You see here pressure from surrounding fluid will be on the element equal and opposite because according to Pascal's law, pressure at this point equal to pressure at this point and equal and opposite from surrounding fluid. So this along the height, pressure acting on the surface will be cancelled out according to law of the Pascal because the Pascal's law states that intensity of pressure at any given point or at the same level is the same everywhere. So on this point, corresponding point are there in another surface. These are neglected. Pressure forces on the along the length of the cylindrical element are cancelled out. So now writing equation for the force balance and how this element is balanced. And one thing that acts, that is a gravity force. Gravity force on the cylindrical surface, on this cylindrical element. So we apply pressure forces. There are different pressure forces at the surface AC and at the AD. So there is some difference in pressure force. So writing a pressure balance equation, a force balance equation along y direction because x direction along the F direction these are cancelled out. This is y direction and this is x direction. Along x direction these are cancelled out, but y direction these are not cancelled out. So sigma Fy equal to 0. So P into A minus P plus del P over del y to dy multiplied by A equal to weight of this element. Because it is an equilibrium, so this pressure difference, force due to this pressure difference must be equal to weight of this, gravity of this fluid element, that is equal to rho A and dy. This is the length. A dy is a volume of this element and rho multiplied by mass and g say multiplied by g, then it is a weight. So now solving this equation, Pa minus PA and minus del P over del Y dy into A equal to rho A dy into G. So this is cancelled out and A is also cancelled out, dy is also cancelled out. So equation minus del P over del Y equal to rho G. You can also write as A equal to gamma. This is a specific weight. So this is equation that we want to derive. This is general equation. This is general equation. And this is general equation. Minus del P over del Y equal to rho G. Rho G are equal to gamma. Gamma here we use for the rho G, that is specific weight. Or you can say minus del P equal to gamma into dy. Are you, because you know that one thing I want to state here, because del P over del Y, simply you can say minus gamma, and you can, because we have taken very elemental change in pressure, and with respect to elemental change in Y, you can write simply that dP over dy. Same thing, because it is only one variable. Pressure is varying with respect to Y. So you can write dP over dy equal to minus gamma, or dP equal to minus gamma into dy. Integrating this equation from dP for reference point from y1 to y2. We can integrate this equation from reference point y1 to y2. How pressure is changing? From y1 to y2, pressure is P1 and P2 equal to minus gamma, and dy changing y1 to y2. So equation will become P2 minus P1 equal to minus gamma y2 minus y1. So P2 minus P1 equal to minus gamma y2 plus gamma y1. Balancing this equation. So P2 plus gamma y2 equal to P1 plus gamma y1. So dividing whole equation with y2 with gamma. Dividing whole equation with gamma. So P2 upon gamma plus y2 equal to P1 upon gamma plus y1. Or you can say P upon gamma plus y equal to, this is a constant. So this is known as a piezometric head. This is known as a piezometric head. So piezometric head remains constant at every point of the fluid. At any point you can say piezometric head of Pa1 upon gamma plus y1 remains constant everywhere in the fluid. This is a property of fluid, that piezometric head remains constant. Take equation here, P2 minus P1, P2 minus P1 equal to minus gamma y2 minus y1. Suppose y1 equal to 0 at reference point, y1 equal to 0 means at datum point, and y2 equal to h, y2 equal to h. Y2 equal means whole length is h. From here to here it is a depth h. From free surface depth of the bottom is h. So what will happen? At y1 equal to 0, you want to pressure P1, and at y2 equal to h, you at y2 equal to h. When we move from here to here, pressure become P2 equal to P atmospheric. So at y2 equal to h, P2 equal to P atmospheric, and P1 equal to P that we want to calculate. So P2 equal to P atmospheric minus P equal to minus gamma. Y2 means H minus Y1 0. So P equal to P atmospheric, P equal to P atmospheric. P balance here, P atmospheric plus gamma H, or P atmospheric plus rho GH. This is required equation. Pressure at any depth you can find out using, if you are measuring pressure from top to any depth, you can use this equation, P equal to P atmospheric plus rho GH. This is general equation, and everywhere we want to calculate pressure at bottom. Pressure at the bottom will equal to P atmospheric plus rho GH. Here rho is the density of fluid, G is a gravitational acceleration, H is a height from sea surface, because we are measuring pressure from this side to this side. So two things we have learned here, that any point of the fluid, piezometric head remains constant, means P upon gamma plus y equal to constant for any point. And another thing is that at any depth we want to calculate pressure. So P equal to P atmospheric at the free surface plus the depth of the fluid, rho GH. So by using this equation, you can find out pressure at any point, and this concept of measurement of pressure is applied in all kinds of measuring devices, whether it is a piezometric tube or it is a U-tube manometer or differential U-tube manometer, any kind of the manometering device. This is concept where we have to apply two things. That is a concept of Pascal's law, and by applying the concept of Pascal's law, we got this pressure. And in depth, we will also discuss how pressure changing with this variation in density, because here we have considered that density is not varying, density remains constant, but when we go up from ground to the atmospheric up to higher height, we see that pressure is decreasing. For that we will discuss separately how pressure varies when we go up in surround, because density of the atmospheric gases decreasing, so pressure will also changes. So this concept is very useful in competitive examinations and for your mechanical engineering, fluid mechanics, and we apply this concept in manometric calculations. Thank you very much for watching, and wish you, I think you will appreciate and share to your friends. And next we will meet and discuss. I think it is in experimental works we have to measure variation with flow measurement in various devices. For example, notches and wear. So next topic we will discuss how we calculate theoretical flow from the notches, and how we can calculate coefficient of discharge and compare coefficient of discharge for V-type notch and rectangular notch and trapezoidal notch. So thank you very much for watching.